colleague Fred Cohen. Fred Cohen passed away 2 days ago. Rest in peace, Fred. Whoops. Okay, now, one moment. So, Rudra invited me to speak in this seminar. It's a bit of a stretch to say that the subject of this talk has anything to do with group theory or triangulated categories. It's algebraic topology, and it's not even what you might, I can't even say it's 21st century algebraic topology, where it's about a calculation doesn't use anything involving infinity categories or anything like that. This is kind of old-fashioned algebraic topology, and it's on the subject of string cobordism at the prime 3. Some of you have heard this talk before. My apologies to you. If you went to the Princeton seminar in December or the UCLA seminar in May, this is basically the same talk with only a few minor modifications. So this is joint work with Vitaly, Lorman, and Carl McTague that you see depicted here in various ways. So string cobordism is Haynes-Miller's term for, I'm having a little trouble with my screen here. Okay, Haynes-Miller's name for the spectrum also known as MO8, which is this Thom spectrum associated with BO8, and BO8 is the 7-connected cover of the space BO. BO is the classifying space for orthogonal vector bundles, and we know that the homotopy groups of the associated Thom spectrum have a an interpretation in terms of cobordism. This was originally proved by Thom in the late 50s, and I believe that's a big part of the reason he won the Fields Medal. And algebraic topologists have been studying variations of this for decades. We look at various spaces that map to BO, such as connected covers, or the class, or BU, the classifying space for the unitary group, or even BSP, the classifying space for the symplectic group. And in each case, there's a Thom spectrum. And in each case, you can ask about its homotopy groups. And these homotopy groups are often amenable to analysis using the atom spectral sequence. And so what I'm talking about today is that kind of calculation. So the homotopy type of MO8 has been studied for quite a while. It was first studied by, at the prime 2, it was studied by Vincent Giambalvo in his thesis in, when was that? Oh, 71. Vince is attending this talk today. I'm very pleased about that. Actually
68.
68, okay. The paper was published in 71. You were a student of Frank Peterson, yes?
Yes.
One of his very first students, I think.
True. Second, I think, or maybe
second.
Third.
Yeah. Anyway, it's very complicated, and this is still not fully understood. This is, if you localize it at the prime 2, it's very complicated. We now know that it admits a map to TMF, which is the spectrum for topological modular forms, which has been studied a great deal in the past 20 years. And this map is surjective in mod 2 homology. Now, at primes larger than 3, this spectrum MO8 is known to split as a wedge of suspensions of the Brown-Peterson spectrum BP, and there is some subtlety in its multiplicative structure, and this was the subject of a paper by Mark Hovey in 2008. So this is at primes 5 and up. So the prime 2 is very complicated and still not understood. Primes 5 and up are relatively easy, and that leaves the prime 3, which is the subject of this talk. And so you could say it's a sweet spot in that its homotopy type is both interesting and accessible. And it was the subject of a paper in 1995 that Javi and I wrote. And about 3 years ago, Carl and Vitaly took up this project again. Now, it is useful to compare this problem with the study of MSO, that's oriented cobordism, and MSU, special unitary cobordism at the prime 2. It's a useful analogy. So I'm going to spend a few minutes talking about that. So MSO, oriented cobordism, is the subject of a paper published in 1960 by Terry Wall. Now, as a comodule over the dual Steenrod algebra, the homology of MSO splits as a direct sum of suspensions of two types of modules. One is a copy of the dual Steenrod algebra itself, which is the homology of the mod 2 Eilenberg-MacLane spectrum. And the other kind of summand that occurs is the quotient of that by the ideal, by the exterior algebra generated by square 1. And that is the homology of the integer Eilenberg-MacLane spectrum. So if you look at this thing as over the Steenrod algebra, you're led to believe that MSO splits as a wedge of mod 2 and integer Eilenberg-MacLane spectra. And the second types of summands occur, there's one for each monomial in a graded ring with generators in a graded polynomial ring with a generator in each dimension divisible by 4. Now, this splitting that the Steenrod algebra leads you to think happens actually does happen. And MSO, localized at the prime 2, splits as a wedge of integer and mod 2 Eilenberg-MacLane spectra. And if you looked at the atom spectral sequence for it, it would collapse from E2. Now, it is all, if you do this at odd primes, then it's known to split as a wedge of suspensions of Brown-Peterson spectra. This was actually shown in the original paper of Brown and Peterson in the late 60s. Now, let's move on to MSU. So this is the SU is the special unitary group. We were looking at the special orthogonal group. Now we're looking at the special unitary group. So this is the subject of David Pangeli's thesis published in 1982. David was my first PhD student. Now, the homology of MSU, the mod 2 homology of MSU is the double of that of MSO. That is, you take the homology of MSO and double the dimensions of everything. So this means that as a comodule over the dual Steenrod algebra, it also has a splitting into summands of two different types. So one of them looks like this. It's the polynomial algebra generated in homology. It's the polynomial algebra generated by the squares of the zetas. And this is the homology of the spectrum of the Brown-Peterson spectrum at the prime 2. And then the other one, analogous to what happened in MSO, is a gadget that looks like this. Now, I'll remind you, at MSO, the second summand had this description here. It's polynomial, its homology is polynomial on zeta 1 squared, zeta 2, zeta 3, and so on. Now we're looking at, now we square everything in sight. So we've got zeta 1 to the 4th, zeta 2 squared, zeta 3 squared, and so on. Now, this is a new gadget. You might think that this is the homology of some spectrum X. Now, I believe that Andy Baker has a proof that there is no spectrum like this. I haven't fully processed your argument yet. But anyway, algebraically, there's one of these gadgets appearing for each monomial in a polynomial ring with generators and dimensions divisible by 8. And let's assume for the moment that there is a spectrum X that has this homology. Then it's easy enough to work out what its atom spectral sequence would be. And we find, and it's easy enough to calculate what its homotopy groups are. And what we find is that it's the homotopy of the spectrum BO, little connective K theory, real connective K theory, tensored with a polynomial algebra on elements known as V2, V3, and V, et cetera, that are related to elements that you see in BP theory. Now, pi star BO is a gadget that has some torsion in its homotopy groups, and that torsion occurs in dimensions congruent to 1 and 2 mod 8. That fact is going to be important to us. Now, here's what the Adams E2 term for this hypothetical X looks like. Now, I've color coded it for to make it for expositional purposes. The stuff you see in white is what you would have if you were just looking at little bo. The stuff you see in white, it represents the homotopy of little bo or connective real K theory. And the towers, the vertical towers, represent copies of the integers, and the little elements like this element here, these are torsion elements. This is a torsion element, a copy of Z mod 2 in dimension 1. Here it is in dimension, another one in dimension 2. Here's one in dimension 9, 10, and so on. And these little white dots occur in dimensions congruent to 1 and 2 mod 8. Now, that's what happens in BO. When we pass to this hypothetical X, we get more copies of the same thing corresponding to monomials in those V's. So the red here is, everything in red is V2 times some element in white. Everything in blue is V2 squared times some white element. Everything in green is V3 times a white element, and so on. So this is a pretty picture, and it's not hard to show that maybe this spectral sequence has differentials, maybe it doesn't. But one important thing to note here is that the thing I'm pointing to right now would be a copy of Z mod 2 in dimension 7. If this X exists, or more importantly, if X was a summand of MSU, then MSU would have to have homotopy in a torsion in pi, a torsion element in pi 7. Now, this is problematic because of a theorem proved by Conor and Floyd in 1966. And they showed that the only torsion in pi star mu occurs in dimensions congruent to 1 and 2 mod 8. So you can't have, MSU can't have a torsion element in dimension 7. So if this spectrum X exists, which it may not, but if it did, it couldn't be a summand of MSU because of this, because that would contradict the theorem of Conor and Floyd. So this element right here, this element is that I'm pointing to, this is eta V2. It would have to be killed by a differential in the atom spectral sequence for MSU. Now, mind you, this picture that I'm showing here would occur as part of the Adams E2 term for MSU. The Adams E2 term for MSU would have this plus more stuff in it, including another copy of this whole picture starting in dimension 8. Anyway, this would occur as a summand of the Adams E2 term, but this element right here can't survive because if it did, it would contradict the theorem of Conor and Floyd. So we've seen that MSU, the homology of MSU has a summand that looks like this. It's this funny polynomial algebra associated with that picture on the previous page, tensored with a polynomial algebra on these y's that occur in every 8 dimensions. And the Conor-Floyd theorem leads to the Conor-Floyd theorem implies that there have to be Adams differentials of the following form. So in particular, Y8 has to support a differential that kills eta V2. So back here, if I was looking at the corresponding picture for MSU itself, there would be a Y8 right here where the arrow is, and it would support a D2 that would kill this red torsion element. All right, so we're going to call those Pangeli differentials. Now, Conor and Floyd, as far as I know, never looked at this Adams spectral sequence. They proved their theorem by other means, not related to the Adams spectral sequence. And Pangeli was the first person to look at this the Adams spectral sequence for MSU carefully. So anyway, this means that MSU does not split as expected into a wedge of suspensions of X and BP. It does not behave the same way that the analogy with MSO would lead you to expect. There are these differentials that occur that don't have any analog in the MSO case. So Pangeli gets instead a spectrum that he calls BOP, B-O-P, that has an additive comodule isomorphism that looks like this. It's this polynomial algebra that we were looking at before, and then you tensor it with exterior algebra on y's where the subscript is an index of, is a power of 2, and you need each of those y's to kill these elements a to vn. Each of these a to vn's contradicts the Conor-Floyd theorem, so they all have to be killed by differentials. And Pangeli showed that there is a spectrum, a summand of MSU that has just the right amount of stuff in it to accommodate the Conor-Floyd theorem. So this is an additive isomorphism, not a multiplicative isomorphism. Now, Stan Kochman, about 10 years later, showed that there is a multiplication on this BOP, and Pangeli knew that BOP supported a map to BO, inducing an isomorphism of torsion in homotopy groups. It turns out that after you take all these Pangeli differentials into account, the only torsion that's left is the white elements back here. Turns out that if you looked at the spectral sequence for BOP, all of these torsion elements, except the white ones, would be killed off by differentials, and the only remaining torsion would be these white elements. And those are the same elements that you see in the torsion of pi star of little bo. All right, now, Pangeli also showed that MSU localized at the prime 2 is equivalent to a wedge of suspensions of BOP and BP. Now, our goal is to prove a similar statement about MO8 localized at the prime 3. Namely, our goal is to prove that it is also a wedge of suspensions of BP and a new spectrum, the analog of BOP, and it's going to support instead of having an interesting map to BO, it's going to have an interesting map to TMF. This is 3 primary topological modular forms. So our name for it is BMP instead of BOP, or bump. Now, how do we study this thing? Well, we have to go back to some early work of Steve Wilson. the space that is relevant here, BO8, localized at the prime 3, this is a Wilson space, by which I mean it's a space that has both torsion-free homology and torsion-free homotopy. This is a very unusual state of affairs. There are only a small collection of topological spaces that have this property, that where both the homology and the homotopy are torsion-free. And they were all classified by Wilson in the in his thesis, which was published in 73. So we know what all of them are. And their homotopy groups were described perhaps in a more explicit way in the paper that he and I wrote called the Hopfring paper that appeared in 1977. Now, given a spectrum E, let's let E sub k denote the kth space in its omega spectrum. A spectrum is a spectrum originally defined as sequences of spaces with maps from the suspension of the kth space to the k plus 1 space, and you can always arrange things so that these spaces are infinite loop spaces. So given a spectrum E, E sub k denotes the kth space in its omega spectrum. And the spaces that the spectra that we're interested in are BP and its relatives BP bracket n. Now, let's let E sub n stand for this number here, the sum of the first n powers of P. Then here's what Wilson shows. BP sub k is a Wilson space for each k, and BP bracket n sub k is a Wilson space provided that k is not too big, provided k is no more than 2 E sub n. And every Wilson space is equivalent, homotopy equivalent to some product of these gadgets. In particular, BPNK is a factor of BP sub k and so on. So these spaces are very well understood, and we know just about everything you might want to know about their homology groups. And we've known this for a long time. Now, so I'm going to tell you a few things about this because we need this to do the calculation that I'm describing here. So EK is the kth space in an omega spectrum. So that's an infinite loop space. And that means its homology with field coefficients is a Hopf algebra. And so there's a multiplication in the homology, and we call that the star product. And there are actually two products that are kind of going to come into this picture. That's why I'm using this funny notation. So this product is associated. This is the fact that EK is an infinite loop space and hence an H space, and that means there's a multiplication in its homology. Now, if E is a ring spectrum, that's our assumption, that means that the multiplication in the ring spectrum induces maps as indicated here. E sub k cross E sub L maps to E sub k plus L in a certain way. And that means that if you have elements in the homology of those two spaces, you can multiply them, you can look at their tensor product, and that has an image in the homology of E sub k plus L, and we denote that by X circle Y, and this is the circle product. So we have the star product and the circle product. The star product happens between two elements in the homology of the same space. The circle product happens between two elements in the homology of different spaces in the spectrum. And it is known to play nicely with the coproduct in the Hopf algebra. We've got ourselves a Hopf algebra. Each of these the homology of each of these spaces is a Hopf algebra, and this star product plays nicely with the coproduct. And if you put all this together, and consider the collection of these spaces for all K, you get a graded space, which I've denoted by E bullet. And this is a graded ring object. Its homology is, I should have said the homology of this graded space is a graded ring object in the category of coalgebras. And we called such things Hopf rings, a Hopf ring. Now, it is known that the star and circle products are related by a distributive law, similar to the distributive law relating addition and multiplication. Star product is related to addition, and circle product is related to multiplication. I'm not going to spell that out here. Yes? Did I hear a question? Okay, now another feature is that if you have an element in the homotopy of the spectrum, then that leads to an element in the H0 of E sub minus M. E sub minus M is by definition the nth loop space of E sub 0. And it's the Hurewicz image of an element in pi's, the corresponding element in pi 0 of that space. So this is, I'm denoting this by square bracket X. X is an element in the homotopy of the spectrum, and that leads to an element, square bracket X, in the 0th homology of E sub minus M. Now, if X is complex oriented, which is the case in the examples we're interested in, then that means there's a map from CP infinity to E sub 2 that has certain properties. And so we can look at how that map behaves in homology. We know what the homology of CP infinity is. We know that it's a copy of the integers in every even degree, and I'll denote a generator of the H2K by beta sub K. And under this map, I'll get an element in H2K of E sub 2 that I'll call B sub K. So we have those elements in the homology of E sub 2 when E is complex oriented. Now, it is known that this element is decomposable under the star product when K is not a power of P. So the only ones we really have to keep track of are the ones where K is, the index K is a power of P. So we are interested in elements having this form. So the multiplication here is the circle product. So the V's, this monomial in V1 through Vn is an element in the homotopy of the spectrum BPN. So we get a corresponding element in the homotopy in H0 of an appropriate space in the BPN spectrum. And we also have monomials in B1, B sub 1, B sub P, B sub P squared, and so on, as I described previously. And the number M here is this number. And the number K that appears here is this number. And we know that the homology of this space is generated by such elements, by elements of this type, as a ring under the star product. And it's subject to a certain relation called the Hopf ring relation that has to do with the formal group law. One of its, I'm not going to spell it out in detail, but I'll tell you, I can tell you one, give you one example of it. If I take B sub P to the T, raise it to the Pth power under the circle product, multiply it by bracket V1, I get this element over here. This is negative B, the same B raised to the pth power under the star product. And this happens in the homology of BPN bracket 2. Now, I know this is very technical and hard to digest if you've never seen it before, and I'm not expecting you to digest all of this, but I want you to know that these techniques are available for studying the homology of the spaces that are relevant to the problem at hand. And now I've got maybe the best thing that's come out of this collaboration so far is the following joke. I'll refer to calculations of this sort as beekeeping. Now, we know that the homology of this space, BP bracket n sub 2k, is a polynomial algebra under these elements, provided k is strictly less than en, but this is not the case when k is equal to en. We still have a Wilson space, but its homology is not a polynomial algebra. This is what I call a borderline Wilson space. Now, in particular, recall that E1 is 1 plus P, or 4 in our case. And so at the prime 3, B08, the space that's relevant to our problem, is the same thing as the borderline Wilson space, BP bracket 1 sub 8. So this is a space where we know the homology, but it's not a polynomial algebra. There's some elements in it some elements in the homology that cube to 0, and it's a tensor product of a polynomial algebra and a truncated polynomial algebra of height 3. Now, here are the first few generators in the homology of this space. They are all expressed in terms of B's, those B's where the subscript is a power of 3, and eventually we need a bracket V1 in the picture. There are certain these elements are certain monomials, or in some cases, two-term expressions in the B's, and I'm calling them X's and Y's. The X's are polynomial generators, the Y's all cubed to 0. So we can work all this out using techniques from the 70s. So we find that the homology of B08 is a polynomial algebra on certain X's tensored with a divided power algebra on certain Y's, where gamma is short for divided power algebra, and that's the dual of a polynomial algebra on a single generator. So for example, the divided power algebra on Y8 is the same as the truncated polynomial algebra on Y8, Y24, Y72, and so on, and the cube of each of them is 0. And there's a certain coproduct structure relating these elements. Now, in addition to this, it's not hard to work out the action of the Steenrod algebra on this thing. The Steenrod algebra in homology acts on the right, and it's not hard to work out how it acts on the homology of B08 and on the homology of M08. So we want to use this to study the 3 primary atom spectral sequence for M08. So let me remind you that the dual of the mod 3 Steenrod algebra has this form. It's an exterior algebra on certain classes known as taus, tensored with a polynomial algebra on certain classes known as zetas, and the dimensions of these elements are as indicated here. Then there is a subalgebra of the Steenrod algebra generated by the reduced power operations, and that is dual just to the polynomial algebra on the zetas. There's also a subalgebra generated by certain elements defined by Milner, and they dualize to an exterior algebra on the taus. The taus are odd dimensional. And we know exactly how to calculate X over this exterior algebra. And the X group is a polynomial algebra on classes known as A0, A1, and so on. And I will abbreviate this polynomial algebra by V. And here AN is closely related to the element V sub n in the homotopy of BP theory, where it's understood that V0 is 3. And this element has Adams filtration 1 and topological dimension indicated here. Now, there's a Cartan-Eilenberg spectral sequence relating these gadgets that looks like this. And the coaction of the odd dimensional part on the homology of MO8 is trivial because MO8, its homology is concentrated in even dimensions. So this leads to the isomorphism that's the second assertion here. So this is a Cartan-Eilenberg spectral sequence that will converge to the Adams E2 page. So it involves X over P lower star of the homology of MO8 tensored with that polynomial algebra V. That's essentially a filtered form of BP theory. Now, so inside this thing, I wanted to look at a certain ideal generated by these elements here. And I will refer to this as the change of rings ideal. The reason for that is one can show that the X over the reduced powers of the homology of MO8 is isomorphic to X over a much smaller gadget of the quotient of MO8 by this ideal. P1 star is it's dual to the subalgebra generated by the Steenrod operations P upper 1 and P upper 3. And it's a finite dimensional gadget. So being able to convert from X over the P star to P1 star is a big simplification. But we can do better. So I'm going to abbreviate the quotient by that ideal J. I'm going to abbreviate that by L. So, and P1 star is this gadget, as I said. So X over P star of the homology of MO8 is isomorphic to X over this much smaller gadget over of this quotient of the homology of MO8. Now, this algebra, subalgebra of the Steenrod algebra generated by P upper 1 and P upper 2 is non-commutative, and it has rank 27 as a vector space, and it has a complicated X group. But fortunately, we don't need to deal with that because of another change of rings isomorphism that I'm going to describe now. Inside, one of the gadgets in here is zeta 2, and it is dual to this element, the commutator of P3 and P1, which can be written like this. Now, it's known that its cube is 0, and it's known that it communicates, it commutes with both P1 and P upper 1 and P upper 3. So let's call the subalgebra generated by that element T, and we know that L is a free module over this subalgebra T. That leads to a second change of rings theorem, which goes like this. We can replace P1 star by its commutator, or I'm sorry, by its abelianization, this gadget, if we mod out if we kill the element T, this T is the Q is the commutator. So we're killing the commutator. So we're making this is like abelianizing a non-abelian group. We get a commutative gadget, and it's 9-dimensional instead of 27-dimensional. Its dual is this. We've gotten rid of the zeta 2. And then L, the abelianization of L, is the subring on which this element Q acts trivially. And it's not hard to figure out what that looks like. Similarly, in the atom spectral sequence, there's a similar isomorphism. You can reduce everything in sight as a free T module. So you can reduce from a X group over P1 star to an X group over its abelianization. And again, the abelianization of L tensor V is the kernel of Q inside L tensor V. Now, so this ring P1 app abelianization is much easier to deal with. And it's a truncated polynomial algebra on 2 generators of height 3. And I'm going to describe some modules over it. So here's one that is this is the first summand that you see in the abelianization of L. So it looks like this. This is a diagram where the horizontal arrows indicate the action of P3, the vertical arrows indicate the action of P1, and the elements themselves are complicated in expressions involving X and Y's defined previously, and the X's and Y's themselves are defined in terms of the Ravenel-Wilson B's. Anyway, these are all known elements, and this is the first summand that we see in in this thing. Notice it is not a cyclic module over P1 app. It's not cyclic. It has 2 generators, this guy in dimension 24 and this guy in dimension 32. The next one that shows up looks like this, and this is a free module over P1 app, over the abelianization of P1. And then here's a third one. Notice, so in each of these pictures, the numbers in red indicate topological dimension of the classes involved. So in the third one, this has 12 elements in it. I haven't tried to indicate what they all are, but 12 elements that are related by Steenrod operations as indicated by the arrows. So here the top dimensional classes in dimension 64, the bottom dimensional classes in dimension 28, and there's a bunch of stuff in between. And this guy is if you just look at imagine this column here, imagine we had just a module with just 2 elements related by P1 in this way. And if you tensored that with this guy here, you would get up to suspension, you get this guy here. So there's 3 types of summands that we see here. And it turns out that those are the only kinds of summands we see in the whole thing. And each of them it's easy to compute the X group associated with them. And it turns out that both the abelianization of L and the abelianization of L tensor V decompose as a direct sum of modules of these 3 types. So we've got a good handle on the E2 term for the atom spectral sequence. Now, it turns out that each time you see a free summand like this one, the one on the bottom here, where each time you see a free summand of L, that corresponds to a copy of the Brown-Peterson spectrum splitting off of MO8. Each free summand, like the one you see here, corresponds to a copy of BP splitting off of MO8. So it's the other ones, the other two kinds that we have to concern ourselves with. Now, here's a picture of the atom spectral sequence showing D1s and D2s. This is the subalgebra of LAP generated by four guys, and they are Y8, X12, Y20 bar, Y24 bar defined previously. So this is a picture of the atom spectral sequence. Now I am there's a class A2 bar cube that I'm removing to avoid clutter. But anyway, this guy here is Y8. This is something called A2 bar. This is A2 bar squared, and so on. This is a portion of the atom spectral, the atom's E2 term, and their red arrows corresponding to atom. This is actually a portion of the atom's E1 term. Their red arrows are corresponding to atoms D1s and D2s. If you take those red arrows into those differentials into account, you get an E3 page that looks like this. The elements shown in blue are torsion elements. The elements shown in white, these towers, are torsion-free elements. Now, so this is a portion of the atom's E3 term for MO8, a portion of it, not all of it. So it looks like this. Then there are some higher differentials that look like this. Here, now before I said I'd excluded a 48-dimensional class called A2 cubed or V2 cubed. I excluded that. In this picture, I'm bringing it in and I'm excluding some other things to avoid clutter. And I get some longer differentials. This one, I believe there are, I forget, D5s and D7s. I forget what all the indices of these differentials. Anyway, there are some longer differentials that have to appear here that are related to the Toda differential in the stable homotopy groups of spheres. And this goes through a larger range of dimensions. Now, when you take those differentials into account, you get to the E7 page, and there are no differentials after that. And you get a picture like this. And this shows the resulting E infinity page with torsion elements in blue. And the torsion elements here coincide with the torsion elements in the three primary torsion of pi star of the homotopy of TMF, which was described very carefully in a paper of Dominic Culberg from 3 years ago. So that is the end of my talk. Thank you very much.
Thank you, Doug. Let us all unmute ourselves and give Doug a round of applause. Okay, if you have any questions or comments to make, please unmute yourself and make them. Alternatively, you can put them in the chat.
Doug, I have a question. You at some point you said your goal was to try to mimic David Pangeli splitting. So can you actually do that or not?
I think so. Now, I didn't describe the answer. The description of the answer is certain. It's more complicated than his description.
Yeah.
But yes, it is possible to do that. There are certain elements in, let's see, now in his case, how did it go? His, he had his minimal summand BOP,
Yeah.
and then he had to tensor that with a polynomial algebra with generators in every 16 dimensions.
Yeah.
So we get a lot of copies of BOP that way. And then there were a lot of copies of BP that you could keep track of. In our case, the minimum, we're calling the minimal gadget bump or BMP, and it gets tensored with a polynomial algebra on classes. It gets tensored with a polynomial algebra where there's a class in every 36th dimension, starting with 72. You don't get
Right.
72, 108, 144, and so on. So you tensor that with our minimal gadget bump, and then there's a lot of summan's isomorphic equivalent to
Okay.
BP that get.
Okay.
that get in
But
there.
can I ask you about BM? How do you say it? Bump.
Bump. Yeah.
Can I just ask you? So in the BOP case, if you look at the map to KO and look
Mhm.
at the fiber has no odd homotopy. Is there an analogous statement here that the map from BMP to TMF, that the fiber has no odd homotopy? Is that true or not?
I'm not sure. I don't. The fiber from. It could be. I haven't checked that, but and the statement is probably that the homotopy of the fiber is concentrated in dimensions divisible by 4. That's what's.
Yeah, but in
Yes.
particular, the homotopy, there's nothing in odd degrees.
Yeah, but it's constant. It's constant. It's not just even dimensional. It's
Yeah.
4. It's everything.
Yeah,
It's
Okay.
yeah. So so my guess is that it may have the same bump, may have the same torsion as TMF, and
Yeah.
but it's got a lot more.
Yeah.
The torsion free part is a lot bigger, which is similar. to
Yeah,
what
the
happened-
torsion free bit is, yeah,
Yeah.
right. Yeah.
But don't hold me that I can't say this.
Yeah.
Check that carefully.
So I had another question. Yes, so Doug, have you or anyone else?
Can I
Who's
ask?
speaking? Who's speaking? I
Luke-
can't see you.
Sorry,
Hill.
I was.
It's Peter Akhmetov. Can I ask, Duke, a few words about motivation? This is physical motivation of such a calculation. You kill all the interesting homotopy group in the bottom, yes, using your covering. And after you calculate something very difficult, very high dimension. But what for? Can you tell a few about it?
Well, I'm a homotopy theorist and I'm looking for interesting spectra that I can understand. And this seems to be one. Now, what does this have to do with string theory, you may ask? And I believe that, oh, Steve says I should stop sharing my screen. Okay, I will do that. Okay, I'll stop sharing my screen. That's better. Yes. Okay, all right, so I believe some time ago, Witten suggested that it would be interesting to look at spin manifolds with vanishing first Pontryagin class. That this would be relevant to string theory for some reason. And so spin manifolds with vanishing first Pontryagin class. Now, if you're talking about spin manifolds, that means you're passing from BO to its 3 connected cover. And then if you're additionally requiring the first Pontryagin class to vanish, then you're up to the 7 connected cover. You're up to BO8. So BO8 is the space that's relevant to the kinds of manifolds that Witten said he was interested in. And that's why, I believe that's why Haynes called this M string. So I can't comment on the physical motivation, but you'd have to ask a string theorist about that.
Thank you very much for your comments.
Who was
That's
that?
true.
Who was that asked that question? I still don't know who that was.
Better?
Could you say who you are? whoever just asked that question, who are you? What is your name?
I can see the name in the chat, in the audience list. It's Petr Akhmetov, but I'm not
Oh,
sure.
Ahmed, yeah. Oh, yeah.
There's a question in the chat, Doug. Can you see?
A question in the chat. No, that wasn't a question. That was a suggestion. That not share my screen.
Neil, did your message come
Yeah,
in a DM?
I put my question in the chat. I can ask it again anyway. So Doug,
Okay, well, I haven't seen anything else in the chat.
okay. Well, Doug, so I was also wondering if you or anyone else had tried to connect this work that you've done with the story about the theorem of the cube and the other kind of elliptic things for TMF.
I'm sorry, what theorem are you referring to?
Well, you know, there's the paper about why there's a map from M string to TMF in terms of cubical structures.
This is the theorem. Oh, are you talking about who is it? And you and Ando and Hopkins, is that right?
That's right, yeah.
Okay. I can't say that I have. That's a very interesting question. I don't have a good answer for it. So you had you had BU6 was in that paper, right?
Right. Yeah, I mean,
now it is
one thing
true.
you can say.
What's that?
Okay. One thing which I think is a conjecture that I don't think we ever actually wrote a proof of this, but if you take MU6, say, take a homotopy of MU6 and you invert 6, which obviously makes it kind of that's the easy case, but
yeah,
take MU6 and invert 6, then that should be the kind of classifying ring for formal groups equipped with a cubical structure.
Okay. Now another thing you can say is that if you take BU6 at the prime 3, it has a decomposition. I'm sure you know this. If you localize BU6 at the prime 3, then it decomposes into BO8 and the double loops on BO8.
Mm-hmm.
So there's certainly so the two things are certainly related. So I think that means that MU6 cobordism at the prime 3 is essentially the same problem as MO8 cobordism.
Yeah.
Thank you, Neil. Any more questions? Anyone?
This is John Rognes. Can I ask about, so the last pictures or slides you had, were those slides for MO8 or for BMP?
They were for a piece, they were for BMP. Yeah, just BMP.
And do you have a description of the homology of BMP involving sort of, I mean, with BOP, there's these exterior algebras on the Ys. So is there corresponding description?
So in our world, the Ys are, instead of being exterior classes, they're cubic, they cube to 0. Now, in Pangeli's world, the Ys were polynomial generators in the homology of MSU, but he didn't need their squares in BOP. So early in the talk, I said there's an additive isomorphism between the homology of BOP and something tensored with exterior algebra on Y8, Y16, and so on. But in Pangeli's world, those Ys are polynomial generators. In our world, the Ys are actually cube to 0. This is a beekeeping thing. This is a thing you can prove with beekeeping methods. So it's a little bit different. The analogy with BOP is not perfect. Our thing is significantly more complicated than BOP because we're at the prime 3 instead of the prime 2, and so you expect more complications.
And I mean, the picture you showed us showed what happens in the first maybe 144 degrees or so, and implicit is the statement that this repeats. So and in TMF there is a homotopy class in degree 72 that repeats. and the square of it is the usual, more commonly used periodicity in 144. So do you know that that comes from MO8 or from bump? Is that how you prove that it repeats, or?
I think you asked me, I remember you asked me that question. Didn't you ask me a similar question a month ago?
I sent you an email about it about a month ago, yeah.
Oh, yeah, okay. I'm still not 100% sure of the answer to that, but I would guess so. But I haven't had time to check that yet.
All right, thanks.
Okay, John. Any more questions for Doug?
So here's another
comments?
question.
There you go.
Is another question is kind of along the same lines as Andy's question. I was wondering that either for BOP to KO or for bump to TMF, do you know if the kernel in homotopy is generated by a regular sequence?
I don't know that. I don't know that.
Okay.
Thanks, Neil. Any more questions for Doug? Well, if there aren't any more questions, let's thank the speaker again. That's all. Yeah. Yeah, we don't have a meeting next week, but the week after that, Neil Taggart, who I believe is here. Yeah, the week after that, Neil Taggart will be giving a talk. So yeah, maybe I'll see.
Do you know what
some of you there.
the topic is?
I don't know. Let's ask Neil. Neil, do you know what you will talk about in 2 weeks? Yeah, I don't know. Yeah, well, the short answer is I don't know yet, but maybe I'll know in a week or so. Okay. Yeah, thank you all of you for coming, and a special thanks to those amongst you who came from very difficult time zones. Okay, bye-bye.